So where we left off in the last video, we kept trying to approximate this purple f of x with a polynomial, and we at first said, well, let's just make the polynomial a constant and set it, it's just going to intersect f of 0 at x is equal to 0. And so that's a first, you could kind of almost think of it as a 0th order approximation of the function. And then we said, oh, well, what if not only do they intersect at x is equal to 0, but let's say that their slope is the same at x is equal to 0, and that's that approximation. And that's about as good as you're going to do with a line, especially as you get close to 0. And we said, okay, that's good, but what if their second derivative is the same? And that's where we ended up with, we added this term here. And I hinted that we'll just keep doing this process. So let me, oh, that's not what I want to do. We could just keep doing this process. And so you could imagine if I want their third derivative to be the same, I could add another term right here, plus, where I know what the value of f of x's third derivative is at 0. So f, I'll write that as f to the third derivative at 0 times x to the third. Now what do you think is going to be down here? What's going to be the denominator? You might be tempted to say, that we'll put a 3 down here. But it turns out you're going to have to put a 3 times a 2, which is a 6, or 3 factorial. Now why is that? Why is that? Well, let me just take a little departure here, and I think you'll start to understand why you put a 6 down here. Why this isn't a 3 and you put a 6. Here you put a 2, but 2 is also 2 factorial, right? 2 factorial is 2 times 1. Right? Hopefully you remember what factorial. Actually, let me tell you what factorial is just in case. 10 factorial is equal to 10 times 9 times 8 times 7 times 2 times 1. So you're multiplying all of the numbers up to that number. 4 factorial is and the numbers get big very, very fast. Is 4 times 3 times 2 times 1. 2 factorial is equal to 2 times 1. 1 factorial is equal to 1. And now this is kind of a weird definition. It comes out of combinatorics, and actually it works for what we're doing as well. 0 factorial is also equal to 1. I know that might be a little unintuitive, and this is just a definition. It's like saying that I squared is equal to negative 1. It is a definition, but it makes things, it makes formulas be more general, I guess is a simple way to put it. But let me erase all of this, because that was just a divergence, just because I realized I was going to use factorial, so you should know what a factorial is. But I think that's a fairly straightforward concept. So going back to what we were doing, I was asking you, why do I put a 6 down here instead of a 3, like we put a 2 here? Well, let's just take this term alone and take its third derivative, right? So if I have this term and it's, f, the third derivative at 0, x to the third over, let me just write 6 as 3 times 2, or 2 times 3. 2 times 3. And that'll make it a little more clear. What's the first derivative here? What happens when I take the derivative once? Well, I'm going to multiply the whole thing by this exponent and decrement the exponent, right? So I'm going to multiply the whole thing times 3 times f, the third derivative, x squared over 2 times 3. So that first time I did it, this 3 and this 3 cancel out, right? That red's looking a little bit too demonic. Let me pick another color. Okay, fine. And then when I take the second derivative, what am I going to get? Well, the 3's gone. Now I just have a 2 in the denominator, right? So I multiply the whole thing by 2 times f prime 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 of 0 times, and I decrement the exponent, x to the 1 over 2. Well, now the 2's cancel out, right? So the reason why you're putting a factorial there is every time you take a derivative, you're decrementing the exponent 1 and multiplying the whole expression by the exponent. So if you're going to take, n derivatives, you're essentially going to be multiplying this expression times n factorial. And so you don't want an n factorial out here. You put an n factorial at the bottom. Hopefully that makes sense. Play around with it yourself, and it should start to make a little bit more sense. So in general, if we just kept doing this process forever, what would the function look like? What would the function look like? And the reason why I'm covering this is because going this way, we're going to be able to prove what I think is the most mind-bending concept in mathematics. And it will make you love mathematics, hopefully. Some people actually, well, I won't go into the spiritual aspects of it, but So what would be this if I just kept saying that, I'm just going to keep taking derivatives and adding them to this term, this polynomial? Well, the polynomial would become p of x is equal to f of 0 plus f prime of 0 x. And let's just divide it by 1 factorial just to make it clear that that's a 1 factorial, right? And that's an x to the 1, right? That's just this term, but I just wrote it a little differently. And this is, you could almost, this term right here, this is f of 0 times x to the 0. I know that's really messy, but hopefully you see what I'm saying. And that's over 0 factorial, right? 0 factorial is 1, x to the 0 is 1, so it's just f of 0. And then plus the second derivative at 0 times x squared over 2 factorial plus, and we just keep adding the third derivative, the third derivative at x is equal to 0 of x to the third over 3 factorial, and we just keep going on, right? So we could do this to infinity, and actually we will do it, and this is called the Maclaurin series. So if we just wanted to approximate this as hard as we can, just to essentially take the infinite derivatives of it, we get the Maclaurin series. So we are going to define this polynomial p of x is going to be the infinite series, the infinite sum. Let's start with n is equal to 0, and we're going to go to infinity. Infinity. And what is each term? Well, the term, let's think of, it's going to be f of, what's going to be f, the nth derivative of f, evaluated at 0, right, times x to the n over n factorial. This is the Maclaurin series, and we'll later learn that the Maclaurin series is a specific example of the powers of the Taylor series, which is a specific example of a power series. But anyway, this might seem very complicated to you. I have all this sigma notation. Just remember, this is essentially just that, and I just keep going to infinity. And if you play around with it, it should make sense. But I think this will become a lot more concrete when I do this with a specific f of x. And this is where it gets cool, in case you don't think it's already cool. So let's pick f of x to be, to me, the most amazing function of them all. If I ever built a shrine or a church or something or a skyscraper, I would somehow make this function show up all over the place, and then years from now people would be awed by the mysticism of it all. But anyway, let's try to approximate e to the x with a Maclaurin series. And that sigma thing, that's hard to memorize. Just remember, you want all the derivatives to be the same. So let's make the approximation of this. So I'll, and we'll actually learn. Actually, I won't prove it. It's out of the scope of what we're doing right now. But the approximation, even when it's centered at 0, actually equals the function when you take the infinite sum. But let's just see what it looks like, because this is pretty cool. Well, actually, let me before we start building the polynomial, let's just figure out a couple of things. So what is f prime of x? Well, that's also e to x, right? What's f prime prime of x? Well, that is also equal to e to the x, right? We have learned, and I actually recently did a proof, that the derivative of e to the x is e to the x. But that always means the second derivative, the third, and the fourth, and the nth derivative of e to the x is equal to e to the x, right? I could take an arbitrary number of derivatives of e to the x, and it equals e to the x, which is amazing. The rate of change of the function at any point is equal to the function. The rate of change of the function at any point is equal to the function. The rate of change, I mean, that's it. I want to just go someplace and ponder it, but I'm too busy making videos. But anyway, back to what we were doing. So what is f of 0? F of 0 is equal to e to the 0, which is equal to 1, right? Well, that's also going to be f prime of 0. That's also e to the 0, which is equal to 1. So all of the derivatives, the nth derivative at 0 is going to equal 1 for this specific case of f of x, for e to the x. And this is why this is so cool. But actually, it actually gets even more amazing. So you hopefully realize that f of 0 and all of its derivatives at 0 are equal to 1. So now we can do the Maclaurin series in the next video. See you soon.